Well, good afternoon, everybody. First, I'd like to thank the organizer for inviting me. At first, I hesitated a little bit before coming because I had a very busy schedule this fall, but I'm very happy I made it because I can witness the growing interest in N2O, and if I can contribute a little bit, I'm very happy of it. So I was asked to talk today about measuring strategy to quantify the effect of management practices on SO2 emissions. Being the last, of course, some previous speakers have mentioned some of the things that I'm going to talk about, so I may go fast on a few, but essentially there may be a couple of things new that I'm going to say, hopefully. So the summary is, I'm going to start with the background here. Some kind of a little bit of an editorial thing, but since I was told I would talk to an audience of recent users, of chambers, I thought it might be good to say a few words about, how long have we been using chambers, how it has used over the years, and also, maybe more importantly, putting them in relation with the Micromet measurements as well. And then we'll get into that strategy I was asked to determine. This strategy for quantifying the impact of management practices on SOL and N2O, I divided it in a few steps. The first one was to set realistic objectives. And again, that will overlap a little bit of what has been said before, but chambers are good at a few things, but not at everything. And maybe they're not designed to answer all questions in all situations. So maybe to get a successful study experiment is to start with objectives that chambers or static chambers or NSS chambers can answer. The other one is to minimize noise, and by noise I mean any other N2O signal that comes from other than the practice. Practices are not the only thing that impact on N2O. There's other things as well. So essentially, I'm going to propose a couple of actions that will help sort of decrease the baseline of the emissions. So just like on a GC signal, decreasing the baseline so that you can distinguish the signal of the practices. And then I see it identify the changes to N2O production and transfer induced by the practice. What I mean by identify is sort of anticipate, what are the expected impact of the practice on N2O? We know that N2O is going to be modified if we modify substrates, if we modify environment. So I think if we want to design the experiment right, we need to anticipate those things. And that has been said before. I don't remember who, but someone mentioned it before. And then once you've done that, the next step and final step of that strategy is to adapt the chamber design and deployment protocol to suit this the situation that we're in. Finally, we're going to give I'm going to give a couple of examples of this strategy applied to N fertilization and tillage, sort of. And for the question period, maybe it could be a good opportunity if you had any other example we could apply this strategy to. Background, okay. Chambers, you see that I have chambers on the left and Micromet on the right, so I'm going to first talk about chambers. Chambers have been used for a long time. They're not new. They've been used at least since the 1920s, maybe earlier. You may be aware of use of chambers before. And they've been used mostly for CO2. Early users and developers were ecologists that used it for subsurface CO2 flux, mostly in natural ecosystems. And it's not because they were used 100 years ago that they were worse measurements than the one we have that we make now. Like this guy, Lundegaard, in the 20s, had designed an automated chamber for soil respiration. Battery operated with a clock as well. That was action a system that will put down a chamber on the soil, pull it up, sample the CO2. So in the 1920s, so it's a pretty clever guy. They've been used almost exclusively for CO2 until the 80s. And now I feel pretty bad. I haven't mentioned some of the work that Dr. Denmead did in the late 70s, because Tom has worked on N2O, but with open chambers, I think, in the late 70s for N2O. But it was pretty much among the first to use the chambers for N2O, together with Matthias in Hutchinson. And I mentioned Gordon Hutchinson here. I think, well, I don't think. Gordon has been the one, I think, who really shook the house and asked the questions that actually made the research community work towards a better way of using chambers for measuring soil surface gas fluxes. And then the 90s, what I call here the dark age of chamber measurements. There have been a lot of good measurements in the 90s, I'm sure. But there was what I would call the N2O rush. It was the beginning of many, many projects dealing with the soil N2O flux measurements. And not all scientists, I think, was ready to use the chambers. And finally, I think this gave rise to, well, this initiated a rising consensus in the last decade or so towards a standard methodology for chamber. So there's a big difference with Micromet. Like very late, I guess, we asked questions, the physics questions and the how to do it right. Well, in Micromet, they derived the mathematical expression of turbulent transfer a long time ago, like in the first half of the 20th century. And essentially, over the years, the methods evolved mostly because of the introduction of better sensors, sensors that has a faster response. So we went from flux gradient to eddy covariance. And it is interesting to say that even today, even if there is some fast response sensor for N2O, they're still mostly used for water vapor and CO2. So if we look at the comparison between the two, is that the Micromet studies was mostly method-oriented. I was raised as a micrometeorologist, and I've worked several years on eddy covariance system and everything. And really, the thing for a micrometeorologist is actually to measure the thing. Well, the chamber studies, I would say, were mostly result-oriented. I suggest that I propose that this was likely the reason for sometimes a lack of rigor in chamber use and the resulting low confidence in several data sets. However, I think things have changed recently, and I think this meeting is contributing to this thing. Now, if we look at the Micromet, and don't take me wrong here. I think Micromet methods are great. I was there. and they're non-intrusive. They integrate spatially. They describe the temporal pattern. They're automated. We need them. But what I want to stress here is that they're not problem-free. Sometimes we think that because the instrumentation is so flashy that you know the physics are impressive and everything, they have their own problems. Like most of the time, they don't close the energy budget, meaning that they underestimate the flux very, very often, maybe up to 20% in many situations. When you derive the equation for the eddy covariance, for example, you assume horizontal homogeneity of the flux. I mean, this is quite easy to assume if you are over a corn canopy, well-watered, you know, and you measure water vapor and CO2. But if you measure soil N2 emissions over a field, it's very unlikely to have horizontal homogeneity. And this, too, would drive a little bit of underestimation in the flux because it does some lateral diffusive flux in the sun. And also, because it's quite heavy in terms of instrumentation, you know, once you're set up somewhere, the trailer is well installed and the tower is there, the power is there, everything. So there's a trend in the literature to have very detailed information about a few sites, you know. So that's another problem related to the Micromet methods. And also, they're not much used for N2O. I looked in the literature, and all I could find was about 40 papers since 2008. That's not too many. So I guess here my editorial comment and the thing is, value your chamber measurements. They have been, they are still, and they will be in the near future important for the scientific community. So that's the end of my editorial comment. So we get to the what I was. So So I'm here now, we're into what I was asked to talk about, the methodology for addressing the impacts of farming practices on soil and tool. What I propose is to do that in 3 steps, and you'll see that it's going to overlap a little bit with what has been proposed before. So the first one is to set realistic objective, understanding the limitation of the chambers, both in terms of performance and also in the labor required and different things. Minimize the noise, I mentioned it a little bit before. And the third one is to anticipate the impact and adapt the chamber design and deployment. So the first one, set realistic objectives, taking into account the chamber limitations. So let's look here on the right-hand side, all the weaknesses, that we all know and experience when we use it. They're intrusive, labor-intensive. They measure over a too small area for a too short period of time if they're not automated. Okay. So that means that you ask yourself, I think, right at the beginning, before you set the experiment, are the chambers the adequate tool? There are some situations that are just too complex for chambers because they're too variable in space, too variable in time, or for other reasons. Maybe Micromet is the better tool for them. And maybe we should let this to Micromet. One example is a spring thaw period. If we didn't have the Micromet methods, we would know much little about it because chamber deployment at that time of the year is very, very difficult. Spatial and temporal variability. What about the pastures? Laura has mentioned a little bit of pastures. What a complex environment. You have the dung, you have the urine patches, sometimes you have both. You have sections that have been compacted more by the animal. You have the animal itself. You are in a marginal land sometimes, rocky, variable, low spots. It's quite a challenge. I think that those who go into there are very courageous. Maybe that's another area where Micromet techniques are more suitable. Snow-covered and saturated soil conditions. We've mentioned the problem of altering and well, changing the plot soil's conditions if we visit them when the soil is too wet. Snow-covered, well, where I come from, I've been into a business for more than 20 years, and I've always tried to avoid wintertime. Now recently, because of a colleague that has much interest, we have get into this. You can just imagine how difficult it is. We have built scaffolds, over the plots, and we go and, well, not me, but my technician, go and he tries to actually make the sampling in the chambers without actually touching, just like Spider-Man, trying to. So it's very, very, very challenging, very challenging. That's for the chamber limitation in terms of their deployment. Now, resources, and that will overlap with Curtis said a little bit. Do I have enough resources? Number of replicates, that's the first thing to set. I usually use 4. Some prefer to do 6 or 8, and the more the better, but never. Statistically, you can do with 3, but it's very, very risky because 3 is still a lot of energy and investment to do, and the risk of failure or lack of significant conclusion is very high. And then you have to decide how many treatments and sites that you include in your study. And again, don't bite more than you can chew. You better have a good description of fewer treatments at fewer sites than being just surface or too much noise on too many topics. Site location. Because you need to go off and think about it. Like if you have a choice and a site nearby and another one that is 100 kilometers away, you better take the one that is nearby because that's the one it's going to be much more easy to visit more frequently and then get a better temporal description of the flux. Also, it's not fun to send your research team for 2 hours or 3 hours a day on the road. I don't think a scientific objective justify a car accident or something. and find a compromise between the sampling load and the sampling frequency. So the bottom line here is, for that first step is that the success of a failure of an experiment often depends on decisions made prior to field work. So take the time to plan your experiment adequately. The second one is to minimize the noise. And I start here with site selection. I have this graph here that when I teach N2O, I present that. So you've seen it in the different forms. That's the way I illustrate it. It's in the middle, you get the biological N2O production and also the gas transfer. And you have proximal factors that attack directly on the biological activity and the production of N2O. You have the substrates, carbon and nitrogen, and the other side you have the environment, the soil environment, the physical chemical parameters. And then you have the distal factors, those who don't act on N2O directly on the production, but indirectly by affecting the proximal factors. So I have grouped them in two here. We've got the sort of, can tell in the environment, like the soil and climate, and also the practice. And today the talk really deal about, or aim about practices. So that illustrates, okay, we all know it, but this illustrates clearly that practices are not the only factors affecting N2O. There's other things out there. So the question is, what if we want to distinguish the impact of practices, the signal of practices, is to see, is it greater than the one from the environment? And to illustrate that, whether the practice have more impact on the N2O than the environment, I'm just showing this slide here that from the summary of Canadian data on soil N2O. We first have, we have a database of over 1,300 cumulative annual N2O emissions. And together with that, we have the soils data, the climate data, and the practice data, farming practices data. You see those 5 parameters here. There's no practice in there, but that explains 71% of the variability in the data set. So you can see right there that when you look at the whole data from Canada, practices have an impact, but much smaller than the environment. And if now you look at the emission factors calculated from that database, you see also that the factors that affect the emission factors most are not farming practices, they are the environment. So the bottom line, the take-home message is variation in soil and environmental conditions may very easily mask the practice-induced emissions. Okay? So when you plan for an experiment, site selection is a key thing. And how can you, in order to minimize the noise there, ask yourself the question, is the site too heterogeneous? Texture, like the same practice on a sandy soil and a clay soil, the response will be an order of magnitude, okay? So just imagine on your site, you have clay spots, sandy spots, so of course those are two extremes, but if texture is varying over the field that you have selected to carry on your experiment, you're in trouble right off the bat just to start. Drainage is the same thing. If you have low spots, you know, water fill pore space is the most notorious factor for influencing N2O. So select an homogeneous site to start with. The second thing is, how do past history of the field could impact on the effects of practices on N2O? I participated to an experiment in Brazil, and of course everything is different there. You have 3 crops a year, and anyway, the professor there, he started his experiment, you know, on the field on which they had plowed under a grass field, a perennial grass field, 10 months before. He had 2 crops from that moment to the thing. And the first cropping cycle that we've done, the control plots were so high that we had very hard time distinguishing the impact of practices. So all kind of things that was done to the field in a recent past that could affect the carbon and nitrogen substrate. Any transient conditions in terms of gas diffusivity, for example, if the site has been recently tile drained and the whole thing is rooting, that's going to produce noise that may actually prevent to see any practice impact. Where I come from, I took an example from Brazil, but where I come from is a dairy farming area, and we had examples when we plow under an alfalfa field in the fall. Forget about anything else about the N2O impact the next year, because it's going to bring available carbon up to 200 kilograms of N per hectare, so saturated. So previous management may mask practice-induced emission by raising the baseline emissions. After site selection, try to find an homogeneous site, but that doesn't mean that we don't want to see an interaction between the practice and the environment. So if you can afford it, it is always very good to add a couple of sites with contrasting soil types. If you have a sandy soil and a clay soil, especially if it's on the same farm, so it's exposed pretty much the same climate, it really makes a much stronger study. The other thing to minimize the noise is to select chamber size. Ask yourself the question, what is the smallest scale at which I need information? If I may give a comment, the most often thing, anyway, the comment I have most often about the studies and the methodologies is, why are you using those small chambers? It's true that sometimes you have to fit the chambers between plants. It's rocky, there are roots. I understand that, no problem. But otherwise, always use a larger chamber that you can handle. Okay? Because the N2O flux can vary as much between a couple of feet than 100 feet. So if you can integrate that local variability in the flux, it's going to reduce the variability and the noise in your data. Now, can I remove the mechanical noise? That's you see what I mean by mechanical noise. So it may be the goal of the experiment to see what kind of variability the operations at the farm scale are actually doing. Like you may want to see how a manure spreader actually spread the manure. But if you apply a small chamber following the spreading of solid manure, for example, well, maybe the N rate for the whole field is going to be 200 kilograms of N per hectare, but in your little chambers, it's going to vary between about 40 to 650. Probably, because it depends if it fits, a little. Anyway, it's going to vary very much and induce a very large variability. So what we usually do when we can is that we treat and we apply the exact amount of the amendment within the chamber. We weight it separately and we apply it manually in the chamber. Of course, if, again, the goal of the experiment is to test, in a real field operation, it's okay, don't do it, but this is a way to reduce the noise in the study. So that's basic, the take-home message here is that each experimental site remove as much noise as possible in order to isolate the treatment effect. The third step is to anticipate the impact of the practice on soil N2O and to adapt chamber design and deployment. So if the practice is to have an impact, it will have to change the substrate availability, or form or whatever, and the environment. So how does the practice impact on the carbon and nitrogen amounts, type, and location? And also, how does it impact on bulk density, water content, and soil temperature? Here I'm going to give an example with a comparison of conventional tillage and no-till. Well, if we want to try to understand the impact of no-till compared to conventional tillage, well, it ties up carbon and nitrogen because usually, especially early after adoption, organic matter is going to increase, being sequestered, so there'll be less availability in CNN. It lowers temperature because of the mulch at the surface, and it keeps substrate closer to the surface. Probably. So this will tend to decrease the N2 emission compared to a conventional tillage. On the other hand, it concentrates the substrates, the carbon and nitrogen substrate, increase the water content, again because of the mulch, and increase bulk density, at least in the first years after adoption, and then this tends to increase. To me, when I want to measure between the two, the key thing here is it keeps the substrate closer to the surface. And what does that impact in terms of adapting chamber design and development? Well, because the substrates are located at different depths, between conventional tillage and no-till, they are exposed to different diurnal temperature cycles and N2O transfer time, because if the N2O is produced at depth and has to diffuse to the surface, as opposed to being close to the surface and diffusing to the atmosphere, is going to be also different, okay? So two different situations here. So I may ask here the question, diurnal pattern in surface emissions may differ between no-till and conventional for those two reasons, because the N2O is not produced at the same depth, not exposed to the same temperature. There may be a lag in between. Let's see here if that is the case. It may be the case, maybe not. I've never checked it. But by looking at the impact of the chamber, of the practice on N2O production, I think it may. So if we measure and if there's a lag, they may produce exactly the same amount of N2O, but just with a lag. So if you measure at this time, you will see at tillage it's more, a little bit less, the opposite, and the opposite, you see. So when you're in a situation when you think that the treatment is going to change the diurnal pattern of emission, okay, it's very important to determine the diurnal pattern first. Because if you go at a fixed time and you measure both, and the only difference between the two is just the lag between the two, then you will report a non-difference. And also, this also has an impact on where in the soil profile to measure pertinent variables like temperature, water content, microbial activity. If you want to relate that to the flux, better be where the substrates are located. The other example here is the manure, use of manure versus mineral fertilizer. If we apply the same approach, I mean, the input available in the manure compared to the mineral, input available carbon is increased for the nitrification. The decomposition of the manure is going to increase the use of oxygen and likely increase anaerobic hotspots and increase N2O. On the other hand, there'll be less mineral N content as compared to the mineral, and it may decrease bulk density because of the organic matter, and this may contribute to decrease. So in this, what I think is key for adapting the chamber design and deployment is the input of available carbon and nitrification. So first, are we on a site that is exceptionally rich in soil organic matter? If that is the case, adding a little bit more is not going to make a big difference. So you may, again, mask the impact of the practice. And the same thing with plowing in an alfalfa field the previous year or something. So the recent history in the field has to be explored. And N substrates, like you've got a mineral one that is readily available right after application, and the other one is manure, that the organic form are going to be mineralized probably later in the summer when the soil temperature is warmer. So let's say this is not saying that this is the case, but let's say that these differences induce a different pattern in time in emissions, with the fertilizer emitting more early after application, and the manure later. So we have discussed a little bit the deployment strategy for the sites, and very often we're going to go more often after the manure, the substrate or the amendments application, and then relax or increase the interval afterward. Well, if we do that, you see that you document much more the mineral fertilizer than the manure emissions. So we have to plan sampling schedules so that both emission curves are equally described. So that's for substrate and environment. Chamber geometry, well, this has been discussed before. Like if the practice induces a special pattern in emissions, you have to adapt chamber geometry and spatial variability. This has been discussed by Laura in the UK, where they opted for decreasing air samples for chamber development, but they checked linearity in the increase, and that this is needed. And also remember that using a linear model may bias comparison between treatments, because the underestimation by a linear model may be different depending on the conditions in the soil imposed by the practice. Also, does the practice impact on chamber performance, like the seal, like tillage versus no-till? We give it an example on the next slide. Solid space gas transfer. Let's say you're comparing a fallow soil with a corn crop or a tall crop, and so you have an open environment for the fallow field and a very calm environment below the canopy, very protected in the crop. And you apply a static chamber with no headspace mixing in both of them, then that is very likely to have a bias by the chamber, because in one case you're imposing a calm chamber environment on a previously perfectly mixed and turbulent transfer. So that has to be considered. The example here in the seal between no-till and moldboard plough, shortly after tillage, moldboard tillage. Moldboard tillage, we take a soil layer and flips it almost vertically or sideways, and there are a lot of cracks in there, major cracks, macropores, that goes all the way down to the plough layer, anyway, the bottom of the plough layer. So if you use a 10-centimeter collar and you put that on the no-till, we have a very good seal, and on the moldboard plough is going to leak like crazy. So what we do is we use 20-centimeter collars that go all the way down to the bottom of the plough layer to make a good seal. So that's an example of how the practice may actually alter the chamber performance. So in conclusion, that's what I was proposing for a measurement strategy to quantify the impact of practices on soil N2O, is that start with realistic objective, minimize the noise, account for the impacts of practices on spatial and temporal patterns of N2O emissions, how carbon and nitrogen substrates are impacted, the soil environment, and then account for these impacts by adapting the chamber design and deployment protocol. Thank you very much.
Thank you very much. I really enjoyed that talk. I particularly enjoyed the editorial. And I know you didn't mean it this way, but it's not, I don't think it's chambers versus eddy covariance. And I wonder if some real advance could be made by doing both at the same site, where the eddy covariance maybe gives you the annual flux, and the chambers allow you to understand those fluxes. Yeah. I also, just a comment, I think that is a complicated conversation because people have different language. Gap filling versus interpolation.
I'm sorry, I missed that. What did you say?
Well, I think the two groups that do chambers and eddy covariance have different language, and it takes quite a lot to overcome that language, but the same problems are being addressed in different ways by those two groups. And I think not only is there something to be learned experimentally, I think there's something to be learned from the two approaches and the crossover of that language that I'd be interested in your comment.
Oh yeah, I totally agree that we need both. And I hope that the message that you remember is that we need both. Combining both methods is not easy though. Like, of course, when I went from micrometrologist to soil scientist, I use both the first question was to compare, and it's very, very difficult because you're measuring with the chambers on very small surfaces, and I was working with CO2 at the time, and the other one is on a much larger footprint. It's very, very difficult to combine both, but to compare both. But certainly that the more means you have to document the flux in a situation is welcome, and it's pretty. For the second part of your question, it's pretty. You're right that there is a problem of communication between the two groups, and it is still, it's not, the problem is not being solved. And I think the interests are not always common either. I really believe that the many in the Micromet community, they are mostly interested in the measurement itself, while the soil people are more interested in the flux and the interpretation in terms of ecology and things like that. I can still see, because I'm not talking in much more with the Micromet community, because we don't share the same interest. And I can understand too, like, just imagine if you do measurement of water vapor and CO2 over a crop, you can relate that to the crop physiology and the solar radiation, the soil water content, leaf area index. There's lots of nice story to make. If you measure for a whole season of soil into emissions using a Micromet, you're committing very expensive equipment over large surfaces, and all you get, but at the end of the growing season, you have this nice fluctuation where you can say, oh, here we applied fertilizer, here it rained, and so forth, and at the end you have a very nice cumulated value, much better than ours. It's definitely integrated over space. But you cannot really rely it to the soil factors, because you cannot really sample at the same scale. So so I think that's why the Micromet community does not make more soil into measurement. It's because they're sort of frustrated with the data sets they get and the mileage they can make out of it. I may be wrong, but I think that's because the fact is that they don't publish that many data sets, because that has started with George Turtle in Guelph in Canada in the 1993, 1994, and I remember Arvin Mosier in 1993, I'm old too, saying, oh, chambers are over. He said that to me. He said, oh, forget about chambers. Look at this methodology, how great it is. Well, we're in 2014, and 98% of all we know about N2O is still provided. Well, maybe I'm exaggerating a little bit, but anyway, the vast majority of what we learn even today is with chambers. Yeah. But you're right. We should sit both committees together and try to figure out why we don't collaborate more. Yeah. Sorry for the long answer.
That was a great answer. Thank you. I'm glad that he asked the question in part because the soil carbon and greenhouse gas community is thinking of doing a workshop next year as well on something, and I'm wondering if maybe that topic wouldn't be a great one to bring those two communities together and with a translator. Could have like the UN, where. Yeah. And you could be the translator. That's how you can come back.
Okay. That's good. Okay.
Any other questions?
Thank you very much. Nope. Yeah.
I really liked your answer, and you're spot on, but I do think that eddy covariance is becoming easier. I'm going from soils to eddy, and it's cheaper now, and I think that a lot of the people who are doing eddy covariance are getting tired of just doing the methodological stuff. And I think there are opportunities now for comparisons. You can't do as many replicates, right? But you can have, a direct comparison and then draw on the literature from the paired watershed comparison type approaches to look at differences between management practices. So I hope that we end up in that way. We won't lose chambers, but I hope that we can do that.
Yeah, I agree.
Thanks so much, Philippe.
Thank you.